Hello everyone. Sorry, please, in case you are having anybody having challenges joining, kindly tell them to sign into a Zoom account first. It may be saying only authorized, only authorized people can log in or something. So it just means that you need to sign into a Zoom account first. That's why we said please open a Zoom account earlier. Yeah, earlier on the meetup page. So just tell them to sign into a Zoom account first, then click on the link to take you there.
So, good evening, everyone.
Hello,
Yeah,
good
then we
evening.
can hear you.
So, can you guys see my screen?
Yes, we can.
So, I would like to introduce Americo because some people that are just joining us from all around the world. So, WWCode is an organization that aimed at inspiring women into the tech. Themselves in their different tech careers. So here's our mission. The mission of Women Who Code is inspiring women to excel in technology careers. So guys, we all know that the tech career look as if it's like a male-dominated industry. Joe, we are not trying to like be in a gender bias. We just want more women to come into the tech industry. That is what Women Who Code is all about. And our vision, a world where women are representative as technical executive, founder, VCs, board members, and software engineers. So we will be like creating a community, a world like where women can stand, can be in position, where women can be founder. Okay, you're talking about founders, VC, board members of big technology company. We want to create it where women too can be represented in that kind of world. That's what we are trying to do. Then we have, this is not updated, but we have over 200,000 members around the world. Then we have 200 plus directors, and we are in 60 cities of the world. And we've had over 1,100 events in the past event. Before the old COVID-19, our event used to be in person. We have had so many events, and our members range from junior to the senior engineer. That no everybody is welcome. Either you are just learning, or you've learned, or you want to like grow more and more. So that's what basically, we are not kind of stereotyping anybody. Anybody is welcome into Women Who Code. And because a lot of time people have asked me that you are saying Women Who Code and you want guys to join. No, that's not the point. The point is just bringing more women. We already have guys, and guys can also join us for our events. And if you see some of our pictures, you see guys, and guys can also come. So everybody is welcome. So today's event, as we all know, is algorithm and interview prep. And a lot of people will have asked that, what is it all about? What is algorithm about? We know if you have maybe gone for any interview trying to like get a software engineer work, you know that most questions that people ask is all around algorithm. People don't really want to see what you build. They just want to see your ability to solve problems. So my name is Damilola, and I'm director for Women Who Code in Lagos Network, and I'm a software engineer. So thanks for joining us, and I'll hand over to my co-director now. Hope are you there?
Yes, I am.
All right.
Okay. Okay. Let's share my slide. Okay. Yeah. Mm, yeah. Um. Yeah. So, welcome to this series. Yeah. So, like, official welcome to the series, and we are hoping and praying that you get whatever benefits you are aspiring to get from this whole series. I mean, we have a lot of things in stock. We have a lot of plans to ensure that this is worthwhile. This is engaging as possible. This is interactive as possible, and we want to ensure that at least 90% of the attendees that will be following us through this, because I know some people would want to drop off during along the way, but I want to be positive that 90% of people joining this call today would follow us to the end of this series and would find it impactful and be happy that they joined. Yeah. So some housekeeping rules. Number one, please mind what you post on the chat session, so that we can be able to see important messages and be able to easily reply to them. I mean, there are a lot of people that will be having issues, or you want to say something important, and we'll be using the chat session majorly for questions, issues, or anything, because while the moderator is speaking or while the facilitator is speaking, we would not want you to interrupt by like unmuting and speaking. So it's very important for you to drop your messages on the chat section first, or if it's something important, you can raise up your hand. Like there's a raise hand emoji on yeah, on Zoom. I think when you look down, if you're using a system or even if you're using a phone, when you look down, yeah, somewhere in the chat section, somewhere on the screen, you will find a raise hand emoji. So you can use it to raise your hand. We would see it and we can call upon you. Then please, whenever you join the call or whenever you're not speaking, which is most of the time, kindly mute so that you don't interfere and cause interruptions in the sessions. Yeah. We have facilitators that will be taking us through this whole journey. And these facilitators are experienced people. What I mean by experienced people, I mean they have taken series and series and series of interviews for different companies. I mean Fortune 500 companies, startup companies, big tech companies. Like they are really experienced people. Like they are really, yeah. I mean, no, I don't know what's writing on my screen. So they are really like they are the best people for the job. I mean, so you can easily ask them any question you want to ask. I mean, they'll be ready to answer you because they've gone through this a lot of time, and some of them already have jobs with these companies. And yeah, so I don't know if we have some of our. I know we have some of our facilitators on the call already. So please, for our facilitators, to be nice for you to unmute, introduce yourself briefly so that the audience can at least match a face to your names. I mean, because we'll be mentioning your names on the Slack session, they'll be reaching out to you when they have issues, and to be nice for them to at least place a face to it. So our facilitators can unmute now and do a short introduction, a brief introduction.
Hey everyone, my name is Okwemuko. Can you guys hear me fine?
Yes, we can hear you.
Okay, yeah, so my name is Okwemuko. I'm a recent graduate from computer science in the University of Lagos, and I'm one of the facilitators here today.
Yeah, so can you, okay.
Hey guys, good evening. Can you hear me? Oh, okay, he's going.
No, so we can't hear you.
Oh, okay. Can you hear me now?
Yes, we can hear you.
Okay. Good evening, everyone. My name is Okolichino. So, also a recent graduate of computer science, University of Lagos, and I'll be one of your facilitators here today. Thank you.
Good evening, guys. Can I go? Oh.
Yeah.
Good evening, everyone. I hope you can hear me. My name is Nsege. I graduated from Electrical and Electronics Engineering, University of Lagos last year. I work as a software engineer and I'll be one of your facilitators for this meet. Yep. Did you get that?
Yes, we did.
Okay.
Okay, who is on the call again? Similenya, are you on the call? Oh, okay. Since some other facilities are not on the call yet, yeah, let's hope they would join us along the way. Okay, so let me go back to sharing my screen. Yeah. Okay. So, I know everybody always has a reason why they want to join something or you want to do something. I don't know your
Hello.
I don't know your motivation. Someone saying something?
Yes, I just want to introduce myself. Hello?
Yeah, okay.
Is someone, hello?
Yeah, we can hear you.
Okay. My name is Naimot Kolaole. This is my first time to join you people. I'm living in Belgium, and it's my first time to start coding something online. It's my first experience. I'm a nurse, so I just wish to change my career. That's the reason why I joined this group to see maybe I can find some interesting something there. So that's the reason I joined the group. So good evening, everyone, once again.
Hi. Okay, hi Naima. Thanks so much for introducing yourself and thanks for joining. Yeah, we really appreciate that. So we may not be able to take everybody, introducing themselves. So earlier what we did was introducing the facilitators, those that will be taking us through this journey so that people could map a face to the name. But thanks so much for joining and for introducing yourself. Yeah. So along the line, later on we would give space for introductions, on the chat section. Yeah. So people can drop introductions or introduce themselves. Yeah, later on, after this. Yeah. So back to my slides. As I was saying, I don't know your motivation for deciding to join this series. Everybody has different reasons why they do things. It could be that algorithm and data structure is one of the courses you need to take in school, or one of the things you are trying to do in school, and you want to expand your knowledge, you want to learn more about it. Cool. And it may be that you're thinking of applying to companies that find it important. Article that find it important, because not all companies think it is important to test candidate skills on these concepts. But other companies, they know what they are doing, I'll put it their way, or the one I've experienced, most of the big tech companies out there, Fortune 500 companies, some big startup companies, some other, even some Nigerian companies that I know of, they require any interviewee or anybody trying to join their company to have knowledge of algorithm and data structures, and they are going to really test you on it. And it may be that currently you are preparing for a technical interview. You're already in the process and you really need to prep up your game. You need to upskill yourself, because the market is becoming very, very competitive with series of layoffs, series of rescinded offers. The market is getting very, very competitive, and you need to do all you can to be able to ace whatever interview you want to go for or you are in. But for this series, we'll be looking at algorithm and data structures concepts as regards technical interviews. A lot of technical interviews out there right now put in so much effort, so much emphasis on these concepts, putting so much testing ability on this, they test you a lot with this in different ways. And so for a typical interview process that I've experienced, many of the people I've known have experienced, typical interview process for these companies that find it important would be probably you submit your CV, you have the CV and application stage, and they'll be looking at things like your LinkedIn, what's your profile like, they'll be looking at your GitHub repo if they want, they'll be looking at your cover letter, yeah. And for this series, we wouldn't be covering anything as regards CV and application. We had an online event recently as regards that, and also I think there is a resource, or there's this course online that Audacity is giving out for free to help you with your CV when it comes to submitting, like you want to get into a technical interview process or you want to submit it to a tech company, how to brace up your CV and how to do your CV. Yeah, I already had a link to the resources section so you could jump on it and use it. Also, the next stage could be behavioral interview where they'll be testing your storytelling skills. They are majorly testing your soft skills, your ability to, yeah, they are trying to test your soft skills and they want to test a lot of things, a lot of things about you that is not technical. Yeah, that kind of thing. Then the coding test. Some companies may not do it in this order, some companies may not do it exactly the way it is. But one thing is sure, you would always have these stages in blue and you would always have these stages in gray. Coding tests where they probably give you a test to take via Akarank or Codility or CodaPad. You're given a time-based test and you're supposed to take it, yeah, a time-based test where you're supposed to take it between particular day, and you have to write codes, you have to solve a problem and submit it. Yeah. And the next one or another one could be phone screen interview. I don't know why they call it phone screen, but I mean, what it just means is that you are probably having an online conversation with somebody, a recruiter or an interviewer, where you are writing codes on not the formal platform you have, where you write code and run your code. No, so the platform usually could be, it can be Google Docs, it can be Repo or any other platform. So something where you won't run your code. So basically, I'm just looking for what your thought process is like, how you can write good code, how you can test good code without actually running it through an IDE or running it through an engine or something. And then the final stage most times is usually the on-site, where you probably go to the company and you have series of interview, which is usually whiteboard. Usually what it means is you are writing code on a whiteboard, just as the name implies, and you are not testing it as usual. You're just writing it, you're seeing your thought process, seeing how you solve problems, seeing how you communicate your solutions to them. And after that, most times it could be an accepted, they give you an congratulatory message. Give you a congratulatory message. And so during any of these stages, it could be that so during any of these stages you can get rejected. I mean, a lot of times you could get rejected, but please don't let it bother you, because yeah, rejections will come. Let me just put it like that. Don't let it bother you. That's why I put it like this. And then I know I've asked myself this question several times, because, you know, so many times when I do some of these interviews and I'm like, you get frustrated, you know, and you're like, what exactly, why exactly are they even like testing this particular thing? Why must they test me on? I mean, I'm not going to be using binary tree, heavier tree, or this thing in my typical normal day-to-day job, even if I get the job. So like, why exactly are you now trying to test me on this whole concept? Because it can really get frustrating and difficult. But I think one thing I've tried to realize is, one, they're trying to test your problem solving skills. How exactly can you listen to a problem? How exactly can you think through a problem and provide a solution? And not just providing solutions, I mean, providing solution to a problem can be in different ways. You can provide a solution to a problem that will take 100 years for it to run. And you can provide a solution to a problem and it will take minutes or even milliseconds for it to run. So those are things they look at. They want people that can solve problem, not just solve problem, but solve problem efficiently. And they look at analytical skills also, in the sense that how exactly are you able to like make decisions? How exactly are you able to like choose things properly? Why are you choosing a dictionary instead of a list? Why do you think it is important for you to use a tree in this section, in this kind of problem? So how quickly are you able to decipher that this is what is important, this is what is needed at this point in time? And the fundamental is important in the sense that you need this concept. If you don't know about this concept, how would you know that you can actually use it to solve a problem? If you don't know a dictionary exists, how will you know that? And if you don't know that a dictionary can solve problems in this amount of time, it is faster. Searching through a dictionary is faster than searching through a list. How would you decide to use a dictionary instead of a list? And then they test communication a lot, because why sometimes they may tell you to use Google Docs or use whiteboard to solve problem is that they want to see how you are able to like explain your solution to somebody else, not that you just want to solve something, provide a solution and it works and nobody understands it. I mean, so how exactly can you communicate whatever solution it is to somebody else? How exactly can you talk to somebody else and explain what you're doing? And for this series, this is the schedule we have in plan right now. Yeah, the tentative schedule. And this is supposed to run every week from now till like, July 19, every week. Hopefully it works out like that. And hopefully we get people to always join in as usual. And a typical normal session would be that a typical normal session would be that we have a lead facilitator that comes to give us overview tutorial about this stuff. And before every day, before every webinar day, we would have given some material or resources for you to read up so that you don't come to the webinar blank and you are staring at the facilitator for what's saying. So you should have some ideas or understand a bit of what is about to be said. And all you do is for the overview tutorial, there is the lead facilitator comes to talk and give an overview tutorial about it. Then examples are given, and then we are going to be breaking out into rooms. Yeah, this is very important thing to note, please, everybody. We're going to be breaking out into rooms after. So the point is, like, maybe we have the overview tutorial for probably 30 to 45 minutes, and then the examples 10 minutes or something. Yeah, depending on how the facilitator wants to do it. And then we break out into room. It could last for 1 hour. And what you are doing is you're solving a typical problem, and you're solving it together with everybody in your room. So there'll be somebody heading it, and everybody's supposed to like solve a particular problem together. The breakout room would be organized in such a way that when you are joining the call as from next week, please kindly always append B or I to your name, in the sense that you're trying to indicate whether you're a beginner or intermediate. Beginner in the sense that, oh, I'm like really totally novice. I'm totally new to this concept, or I have just little idea about this concept. Intermediate means I've done questions on this concept before. I've done series of questions, at least I've solved easy questions before, and at least I have a bit of idea about it. So why this is important is that so that whatever question or whatever thing you're solving with people that, have a bit of same level of knowledge with you. So there's no this zigzag flow of communication in the room. Yeah, so please, this is important. Take notes. From next week, kindly append B or I to your name, so that when we are assigning people to breakout rooms, we can easily do that. Yeah, easily do that efficiently. And yeah. So when you get to your breakout room, a typical solving process would be, which is a normal solving process you could always use, even during your interview or anything. You listen to the problem will be given by the person leading the room. You ask questions if you need to. It is important you ask questions, because the problems are always open-ended problems, so that they won't go into detail. So you need to ask questions to be able to bring out the detail. Then you could draw out your own example on paper or whiteboard or anything to share. Then you state out a brute force solution. This is done together in the room by everybody. Then you guys find an optimized you guys find an optimized solution. Yeah, this thing is wrongly placed. Okay. find an optimized solution, then you implement it with whatever programming language you choose to implement with it in the room, and then you test it. And all this whole process, every single thing should be 1 hour. Yeah, I mean, I know it's too short, but we need to always work according to like time. I mean, we don't want to always drag this too long. Yeah, language. I know that is always like a question. People will be like, oh, so what language are we going to be using? What language is actually good to use in an interview or something? For now, I'm going to be leaving it up to you in the sense that when you guys break out to your room, you could always choose the language you want to use, depending on depending on the people in the room. But it's always important to always choose a language that can be easily understood, that, I mean, as language, because so many times, not everybody, we can't always say for a short, say that everybody in the room will know a particular language. I mean, everybody may want to use, you may want to use Python, and not everybody knows Python. So always choose the language that, at least even if the other person does not know the programming language, you can still follow. So like it is explicit, it is easily understood, then you can easily use it. In the sense that you can always write things in shorter lines of code. You don't have to like create class for every single thing when you want to just return 2 values or something. So like those are things to consider when you are choosing the language in your room. They're very, very important. And then these are resources for you to use. Number 1, this is our Slack workspace. It's important for you to join this Slack workspace because in case you have questions or anything and you want to reach out to people, the only avenue you can reach out to facilitators now is via the Slack workspace. So please do join the Slack workspace. Join the technical series, I think that's the name, channel, so that you can easily communicate with people and get information as regards the series. Then this is the Udacity course I talked about how to show up or refresh your resume. This is a post I made some time ago about how to have a good resume for an internship position, but you can still use it for even if it's a graduate position or something. How to, like it's just very easy to understand, and you could always also look at it. Then Cracking the Coding Interview, it is a very important book I would love you to get. It has a lot of questions, it has a lot of step-by-step way, as like it is very important for you to get it for this series, so you could start and follow us up as regards each concept every day. Every concept has a chapter in the book, so you could follow us up. Then some other sites are Akarank, LeetCode. This is where there are a lot of problems you can easily solve, and yeah, problems in different categories for different levels, and you can easily use it to continue, because I mean, practice makes perfect. You can't just be coming to the webinar every day trying to understand and get everything in within 2 hours or less. So you need to at least always do a lot of work on your own. You need the LeetCode account. You need LeetCode or Akarank where you can do practice problems a lot. And so one quote I would love to drop with you is, just like I said earlier, there's a lot of reason why you must have decided to join this series. There's a lot of, something must have motivated you to join the series. And trust me, along the line, things are not going to get easy. There's a time you would probably join your room, you get to your chat room, and the question is totally out of this world. Like, you can't even understand the problem, not to talk of providing solutions to it. And like, why is everybody getting it? Like, okay, is it just that, is it me, or what exactly is happening? Or along the line, you may just feel, man, it's like, this thing is not for me, and you want to drop out, or you want to go back, you know what, it's not my fault, man. It's not every company that will ask me and go in my data structure. Well, Jare, let me go my way. All I just want to say is, the motivation or that thing that motivated you to join the series, the reason why you feel this is important for you, let that always be in your head, so that whenever you feel it's time to give up, it's time to quit, you can always remember that reason, and it will keep you going. And with that, I come to the end of this session. Yeah, you can find me on Slack with this name, and you can find me on Twitter if you need to like reach out to me, say anything. But most importantly, Slack. If you want to reach out to me, please reach out to me on Slack. Yeah, this. Yeah. Thank you. So today we are going to be, if you checked the schedule very well, one important concept we are going to be learning today is the big O concept, big O notation. Yeah, like that is really important. Like that is very important. And the facilitator for today is Timileyin, and he's going to introduce himself when he comes. I don't need to talk too much, but I need to confirm if he's on this call. Timileyin, are you on this call, please?
Yes, I am.
Oh, okay. Yeah, I'm going to share the slide. Every slide we are going to be used will be shared on the Slack workspace. Every slide, every resource, question, or anything, communications will start going on the Slack workspace as from today. Yeah. So we'll be having Timileyin now on line. Yeah, Timileyin, let's have you and let's listen to you.
Everyone, can you hear me?
Yeah, please share your slides. Yeah, share your screen so that we can see your slide.
Okay. Okay. Hello, everyone. My name is Timileyin. I'm a recent graduate from the University of Lagos, Department of Computer Sciences. I graduated last year. And yeah, I've done a couple of interviews and a couple of rejections and a couple of offers also. Yeah, I think that's about fine. So today we'll be talking about the big O notation, as Hope has mentioned earlier on. The big O notation is something that we use a lot in algorithms and in technical interviews when we solve technical questions. Big O notation is this concept that comes up a lot. So we're going to be talking about it today. We're going to be talking about how we can get the big O notation of a particular algorithm. Once we say an algorithm, how we can know the big O notation, how we can basically understand why an algorithm is better than another algorithm in terms of probably time or in terms of space. But today we'll most likely be talking about just time, basically. Okay, so we have an analogy. So let us imagine that I want to send a file. Yeah, so I want to send a particular file to a friend of mine. And this person lives in the same city as me. So I decided that I was going to mail the file to the person. So I said I was going to send a mail to the person, send an attachment, and the attachments will contain the file. So that sounds like a reasonable decision, definitely. That really makes sense. But then if the file is as large as, say, 1 TB, for example, which is the example that's in the slide, it's going to take about 12 days to send that file with a speed of 1 megabyte per second. So if my internet is 1 megabyte per second, it's going to take 12 days for me to send just that file of 1 TB. But it seems that the best way to do this really is, if I have 1 TB, is just for me to just drive to the person's house and give the person the file. Just put the file inside one, I don't know, the file is inside maybe one flash drive. I'll just drive to the person's house and give the person the file. Now, driving to the person's house might not take up to 5 hours, or might not even take up to
Sorry, like Timileyin, sorry to interrupt you. I don't know if it's just only me, but your slide is not changing. Is it just me?
No, it's not changing. I think
your slide is not changing.
You need to click on.
Yeah.
Okay. I think it should be changing.
Yeah, you need to share screen.
Yeah. Awesome.
Yeah.
Okay. So you guys can see it now, right?
Not yet.
I think my internet is terrible. Jesus.
We can see the first slide. Hello,
it's just the first slide. It has not changed.
It's not moving
Now can
when
you see
you
this?
like. Yeah.
Yes, we can see. Yes.
Okay. So it makes sense. So I'm going to start again. I'll start from the analogy. Okay.
Yeah. Go to the
Uh,
analogy. You're not seeing that
You
yet.
okay,
go to
fine.
the analogy, or you can present. Is there no way to present the slide?
I am on
Okay.
the analogy, farms. I think my internet is just terrible.
Okay, it's not presenting. It's not going.
Yes, for some reason it's not going. I don't know. Okay. So can you guys see this now? I hope my
Yes.
internet will help me. Okay. Okay, so as I was explaining before, let us take the analogy again. Say I intend to send the file to someone, to a friend of mine. I intend to send the file to Hope. And Hope lives in the same city as me. I don't know, even if let's say I live in Lagos and Hope lives in Ogun State, for example. But then the logical decision, like what makes sense, if I want to send the file to Hope, is probably send it on WhatsApp or send it on Gmail, or I don't know, probably drop it on Dropbox and then Hope will download it, something like that. But then if the file size is say 1 TB, for example, it will take 12 days to send a file of 1 TB at a speed of 1 Mbps. I know in Nigeria, like internet speed is terrible, and 1 Mbps is still a very, very good speed, like 1 megabyte per second. It's going to take you 12 days, more than 12 days actually, to send the file of just 1 TB. So looking at this, I think it will make more sense to just drive to Hope's house and then drop the file with her. So I just drive to her house, probably the file is one hard drive or something, and then hand it over to her. That really makes sense. And the problem with sending with email, it's not that sending with email doesn't really make sense, but the problem with this is the time it takes for me to send the file using the internet is directly proportional to how large the file is. So if I'm sending a file of 2 KB, for example, it will make no sense for me to go and to drive to Hope's house and give it to her. It will make no sense for me to just send it, because that will take like some milliseconds. But as the file size increases, the time it takes for me to send that file to Hope would definitely increase. And then once you are doing this, it just makes more sense for me to just drive to Hope's house, because no matter the file size, it's still going to take me that same 2 hours to drive to her house for her to get the file. Do you get? If it's very important, if Hope needs this file, like Hope needs it as soon as possible, then it just makes more sense for me to just drive to her house and just give it to her. So this is something that basically represents something in algorithms, for example. So the first one, the time it takes for Hope to receive the file is directly proportional to the file size. For the second one, it is constant. No matter the file size, 20 petabytes, 10 yottabytes, it is still going to be the same 2 hours that it takes for him to drive to our house that Hope would use to receive the file, unlike sending it via the internet. So in academia, we have different types of things that we use to measure time complexities, that we use to measure complexities, basically. And BIGO is just one of them. But BIGO is like the most popular one that we use. So in academics, for example, BIGO is just used to represent like the upper bound of a function. So say if I have a function n, for example, 2n is an upper bound for n, because it means that no matter the value of n, in as much as n is greater than 0, no matter the value for n would never be, n would never be greater than 2n. That makes sense. Since n is an integer, a positive integer, mind you, it means 2n is always an upper bound for n. So BIGO basically tries to represent an upper bound for a function. That is all. That's all it just does. Just sees a function and then gives it an upper bound. So if I have a function, say 2n plus 1, an upper bound is 3n. Though we can have many upper bounds. 4n is also an upper bound. N squared is an upper bound. All those ones are still the big O notation for 2n plus 1. You get? So if I have 2n plus 1, like I said, the big O notation for 2n plus 1 can be let's say 4n, can be n squared, can be something else. In as much as an upper bound, then makes sense. Why big omega is basically used to represent the lower bound of the function. So we have a function and then how to get the lower bound such that the function would never be less than that particular function. So if I have 2n plus 1, for example, then 2n is like the lower bound of 2n plus 1. No, it's the lower bound. It's a lower bound, sorry, of 2n plus 1. We also have n, when n can also be a lower bound, and so on and so forth. So big omega is used to represent the lower bound of a function. Simple. So I have this visualization here, and then we just drew 3 graphs. So we have one for 2n plus 1. I hope you guys can see it. We have 3n, or we have 4n. And now, when we look at it, you can see that for, say, the function 4n, which is basically like the yellow line there, the 2 functions under it, which is 2n plus 1 and 3n, are lower bounds of 4n. 2n plus 1 and 3n. I'm sorry, there's a mistake in the slide. 2n plus 1 and 3n that should be pointing to lower bound of 4n. So 2n plus 1 and 3n are like lower bounds of 4n. Because when you look at the graph, you can see that 2n plus 1 and 3n are always lower than 4n. Like there is no way, the way the graph is going, there's no way, since it's a straight line, that 2n plus 1 and 3n would ever cross or ever get past 4n. Likewise, for 2n plus 1, we can see that the upper bounds are like 3n and 4n. 3n and 4n in this graph are like upper bounds of 4n, of 2n plus 1. Because no matter what happens, 2n plus 1 will never catch up. It will never have a value that is greater than 3n or 4n. So in the industry, why is BIGO important? Like, why did I just mention about upper bounds, about lower bounds, about knowing some things and things like that? Like, why is BIGO even important in the first place? So the reason why this concept is important is it is not enough for us to just write codes. We don't just write codes that just work. Yes, fine, we want to write codes that work, definitely. We don't want to write bugs. We want to write codes that work. Our codes should work. But then it is not enough for our codes to work. We also want our codes to also be optimal. We want them to perform optimally. We don't want something that, say, should use 5 seconds to run. We don't want it to run in 10 years. Like, for example, imagine you're Googling something now, and then it takes like forever for Google to just give you results. When our internet is slow, the thing frustrates us. Now imagine that we have blazing fast internet, and then I just want to search for something on Google, and then it's taking like 2 minutes just to open. We get frustrated. I'll probably just use another product. Now, like, this is very, very important in the industry because we don't want to get our customers frustrated. It is not just enough for our codes to work. We also want to give them their results as fast as possible. We want them to see the result like ASAP, like as they are clicking on it, they should be getting the result. That's why when we're writing codes, you have to think about other things other than just what we're writing. So say I wrote something, for example, maybe we were writing web app or something, and then we're testing it, and then, okay, we see this makes sense. But then we start thinking about, okay, what if we have 10,000 users? What if we have 20,000 users? What if we have 100,000 users? Then we might have some problems. So we need to consider the type of algorithms we use. And then for us to even know how efficient our algorithm is, we need to know the BIGO notation for the algorithm. So that is why we're studying this concept. So one more thing before I move to the next slide. In the industry, BIGO notation is more important than the BIGO mega. Now, I mentioned before that BIGO is used to represent like an upper bound. So if you look at it, an upper bound could be like a worst case. Like a worst case. Let's say, let's bring that function now into Google search, for example. Say Google search runs on the function say 2n plus 1, where n is like the number of users that are using Google search. And then the 2n plus 1 will give us the time that each user will get their results. So an upper bound for 2n plus 1 can be like 3n. So we are sure that worst case, no matter what happens, 3 times the number of users that we have on site is the time that you are going to use to get your results. So if you have 4 users, no matter what happens, less than 12 seconds, you would get your results. If you have 20 users, no matter what happens, less than this, you get your results. So BIGO notation helps us to like, gives us like the worst case scenario. That's in the worst case, this is the time I'm going to get my results. Why BIGO mega basically works on best case scenarios? Because of it basically helps us to like lower bounds. So it helps with best case scenarios. Say you tell us that the best case scenario is that no matter what happens, in 2 seconds, the users will get their results, or in 2 times n seconds. So if I have like 4 users, say in 8 seconds, like users cannot get their results faster than 8 seconds. But really, I don't really care about best case scenarios. I don't really care about, I want the worst case. I want like when, like what could happen? Like what's the thing that can happen in my algorithm? What's the worst thing that can happen? No matter what happens, I still want my users to get their results in like say 20 seconds. And that's why BIGO is more important because it helps us with that basically. It gives us a function that we can use to know when our users can get their results. Something like that. So now let's just go into algorithms, and then let's just check. A very simple algorithm. Once again, I'm sorry, I don't know. The formatting is just all over the place. I didn't use this. I used Google Docs. So I want to see.
Timilane.
Yeah.
Should I help you share? Like, should I share this? Should I share my screen for you? Like using, should I share your slide via my screen?
Can you guys see this?
No, we can't see.
You cannot see any analogy to nothing.
Okay, yeah, we can.
Makes sense. Oh, God. This is serious. And you can see the next slide now.
Yes. Next slide.
Okay. This is interesting. But no worries, we'll continue that.
There seems to be a black, there seems to be a black something, like clearing it or covering it.
I can't see that.
Yeah, we can see it. Like there seems to be like a black this thing.
Yeah, Tim, I think you just need to move your members list, your Zoom members list.
Okay.
Jesus Christ is Lord. So I think
like maybe just close
I appreciate that.
You're welcome.
Thank you very much. I'm sorry, I've never shared slides on Zoom, so sorry for this.
It's fine.
Okay, so let's continue. So let's look at this. Let's also look at this code. I don't know if I've written pseudocode, but I just decided to write something in Java because I think most people might know Java. I don't know. Okay, so this thing is like linear search, right? So we have a function to the left that takes an array and takes an element. And the intention of this function is to search for this element in that array. Simple and short. So the function takes an array, takes an element. I want to check if this element is in my array, I'll return the index of that element. But if it's not in my array, then I'm just going to return -1. So now looking at it, we can see that I initialize the variable n, which holds the array length, and then we're iterating from 0 to n. So we just have an instance checking if the value, our current value, array I equals element, then just return the index. Then at the end of the for loop, I'm sorry, the thing is just not indented well. At the end of the for loop, then we return -1. So looking at this, the best case for this algorithm is if element is the first element or first value in my array. So if element is the first value in my array, that for loop that is there will run just once, right? Because the first element is 6. That'll be the first, that'll just be the right element, and then it's just going to return 0, the index. So in the worst case scenario, in the best case scenario, that for loop will run just once. No matter the size of the array is 200,000, that for loop will run just once. But in the worst case, the element would be the last element in the array. So if the element is the last element in the array, then we have to go through all the elements before we can return a value. So go through all the elements in the array and then return possibly array.length -1. Basically just return the last index. So it means that in the worst case, the time we're going to use to get a result is dependent on the size of the array. Because look at it, if the array size is 2, for instance, and let us say a for loop can run like, let's say each iteration takes 1 second. It means that if my array size is 2, in the worst case, I'll get my result in 2 seconds. In the best case, I'll get my result in 1 second. But if the array size is 100,000, then in the worst case, I'll get my result at the 100,000th second. Do you get? And the best case, obviously, I'll get my result in 1 second. Now, you can see the reason why I said we don't really care about best cases. Because in the real world, really, when I'm searching for an element in an array, like what's the probability that that element would exist? It would be like the first element in the array. It doesn't really happen. So the worst case of this is either the element is the last value in the array, or basically even the element doesn't exist at all. So it means we iterate over the array, everything that is there. We iterate over everything. And then probably now return the last element or return -1. So the time it takes for this function to execute is tied to how large my array is. If my array is so large, then this function will basically take time take more time than if my array is little. Now looking at this graph, let us see this graph. Now the y-axis represents the execution time. So we assumed that each loop takes 1 second. And then the x-axis represents the array size. So if I am going to use, say if the array size, looking at how the graph is going, as the array size increases, the execution time also increases. It's actually kind of sharp. I can see the same goes. When my array size is 1,000, execution time is like 1,000 seconds. When my array size is 800, execution time is like 800 seconds. So you can see as my array size is increasing, my execution time is also increasing. Now let's now look at one other algorithm that is quite popular, which is called binary search. So binary search in sorted arrays. I'll try my best to explain a little about binary search. So binary search in sorted arrays. So let's assume we have an array that is sorted. Yeah. Since the array is sorted, we're sure that all the elements to the right of the first element, they are greater than the first element, greater than or equal to the first element. Right? So if I am looking for, it's like a dictionary. Hey, let's look at a dictionary. A dictionary is in alphabetical order. So when I want to open my dictionary, I'll basically say I'm looking for a word, say pivot, for example. I'll just probably open somewhere in the middle and then check for what I see. If I see M, I would know that P is still in front. And then just open again. Like I would open from M to Z. That's what I'm just going to open. I'm just going to open again. Right? And it becomes way faster for me to get my results. Imagine if our dictionaries were not in alphabetical order. Then it means that for me to get a word, I have to really go through all the words in the dictionary. In the worst case, I'll probably have to go through all the words and then the word will be the last one. But now that it is sorted, I really don't have to go through all the words. I just need to just probably like bisect, probably like open to the middle, check what word is there. Say the word starts from M and what I'm looking for starts from Y. I know that it's in the right side, right? It's between M and Z. So M and Z again, I'll just open again, check. The word I can see there is Q. Okay, then I continue checking like that and it makes more sense. So that's how binary search works. So the array is sorted. The binary search will just say, okay, what am I looking for? I'm looking for an element. Let me go to the middle of the array. Now, if the element I'm looking for is less than the element at the middle of the array, then I'm sure that the element I'm looking for is to the left. The element I'm looking for is to the left. It's basically from the beginning of the array to the middle. That's where it's going to be. It cannot be to the right again because all the elements to the right are greater than all the elements, and greater than the elements in the middle. So then, I'll take the array from index 0 to the middle, and then bisect that again. Check the middle of that one. Check, okay, the element I'm looking for, is this greater than the middle of the left side? If it's greater than the middle of the left side, then I know it now has to be between the new middle I just found to the former middle. Do you get? And then I do that bisection. So now, let's imagine. Now, let us just see then let's say I drew a graph for the execution time for that algorithm. And then it's the same, I use the same array size as the linear search. So looking at it, when our array size is 200, if we trace the execution time, it's going to take about maybe 9-point-something seconds for binary search to get the result. But like linear search, that would have used about 200 seconds to get the result. That's way slower. Now looking at it, 1,000, when my array size is 1,000, binary search is going to use just a little above 10 seconds to get the result. But then if you go to the former slides, linear search was using about, I think, 1,000 seconds. Now I drew another graph that basically compares linear search with binary search. And because of how little binary search does, because of the little time that it uses, you barely can even see the line on the graph. You can just see just that tiny blue line there. And then look at it. When our array size is 1,000, see the line, so it is, the time it's using is just very, very little. Unlike linear search, which is using like 1,000 seconds. So now to the right, linear search uses about 1,000 seconds when the array size is like 1,000. But binary search uses just like 9.99 seconds. So let's assume my array size is 100,000. Linear search will use 1 day and 3 hours. While binary search, in the worst case, would use 16.61 seconds. In the worst case, it's going to use 16.61 seconds. While linear search, in the worst case, will use 1 day and 3 hours. So, okay, let's just continue. So let's talk about common runtime complexities. Yes. So, we're going to focus mainly on big operations and mainly on just runtime. We're not talking about and time complexity basically, not space complexity today, just big operations and time complexity. So now we have some things that we call O of 1 operations. O of 1 operations are like constant time operations. If you remember the analogy I gave the other time about me driving to Hope's house and giving her the file, I said no matter the file size, Hope will still get it in probably 2 hours. So that's a constant time operation. Like no matter the inputs, no matter what happens, I am guaranteed to get it at this particular time. The time doesn't change with respect to the inputs. The time will not change at all with respect to it. So no matter the file size, if the file size was like, I don't know, 20 terabytes, I would have still driven to Hope's house and give her in say 2 hours. Now, if you have any questions, please, I would like us to probably like write it down, and then at the end of the presentation, I would answer all the questions. Or we could type some questions in the chat box, box, and then some of the facilitators also would answer. So, if the I don't know, the file I want to send to was like 20 terabytes or something, it's still going to take 2 hours. Nothing will change at 2 hours. But sending via the internet is going to increase as the file size is increasing. That's just what happens. It's going to increase as the file size is increasing. So that's what O of 1 operations are. O of 1 operations are operations that no matter what happens to, this is the time that's going to take. For example, A plus B. A plus B, or say if A equals 0, want to compare if A is equal to 0. That's a constant time operation. Even if A was 10 million, it still doesn't change the fact that it's still going to take that little amount of time to run. It's still going to run at the same time as if 0 equals 0. Same time, it's not going to increase at all. And now, assuming that I'm hoping that we are programmers, so the time that it takes for us to search for a key in the dictionary is also a constant time operation. No matter how, and when I mean dictionary, for people that are not really programmers, I don't really mean dictionary as in dictionaries of words. I mean like hash maps in programming. So, no matter the size of that dictionary, if that dictionary contains 1,000 elements, it's still going to take a constant time for search for a key in that dictionary. So that's what O of 1 operations are. Constant time operations. A plus B, C equals A plus B is a constant time operation. Int A equals 0 is a constant time operation. All those operations are just constant time operations. And we call them O of 1 operations. So this is an example. So we have a function that adds 2 numbers. That is a constant time operation. Now, we also have another function that prints the first 100 numbers in an array. Now, we're assuming, I didn't write it, but we're assuming that the array's size is greater than 100, greater than or equal to 100. The array size is greater than or equal to 100. Now, this for loop that we have here is going from 0 to 99, and it's printing 0 to 99. This function would print 0 to 99, no matter the size of the array. In fact, I'm not even using the array here. No matter the size of the array, this function will just print 0 to 99. Even though the array is 1 million, this function will still print 0 to 99. So no matter the size of the array, this function will still run the same time. That's what it's still going to use. It's still going to run the same time, using the same time as if the array were, I don't know, if the array size were 1 million or 10 million. No matter what happens, it's still going to use the same time. So let's go to linear time. The other time we talked about linear search. So let's look at what we call linear time. So linear time is like represented with O of n. Now you might ask what's the meaning of n. So if we have an array, for example, that array, we are assuming the array is of size n. So this basically means that the time is going to take for your algorithm to run, or for the function to run, or for the method to run, basically, is dependent on the size of the array in a linear fashion, in a linear way, just dependent on the size of the array in a linear way. So as the array is increasing, the time that's going to take also for the operation to be performed would also increase. Just like linear search that we talked about, that if the array is of size 10, then say each iteration takes 1 second, then it's going to take 10 seconds. If the array is of size 1 million, it's going to take 1 million seconds. So looking at the function, I said int n equals array.length, so n is only array.length. And then I'm just summing all the elements in the array, and I'm returning sum. So this would go through all the elements. That function, you can see the for loop already. It's already going through from 0 to n minus 1. So it's going through all the elements in the array, and then it's adding them and returning the sum at the end of the day. So if my array just contains one element, then this for loop will run just once. Whereas if my array contains 1 million elements, this for loop will run 1 million times. That's why. So it means that this function is dependent on how large my array is. And I've assumed that my array size is n. So I say this function is an O of n function. And then the operation I'll perform is an O of n operation. So looking at it, I said the in sum equals 0 is a constant time operation. That's just represented by C. C just means constant time. So it means it's a constant time operation. Remember, we discussed that in the last slide. In sum equals 0. Doesn't depend on anything, just a constant time operation. Whereas the one inside, that is sum plus equals array I, this really would run n times. And this one is going to run n times. We're assuming n is the size of the array. This is going to run n times because it's inside the for loop, and the for loop basically goes from 0 to n. So this for loop goes from what? 0 to n. So this will run what? N times. And then the return statement at the end of the day is also a constant time operation. See. Now when we add everything together, remember I said constant time operations are basically written as O of 1. So when I add O of 1 plus O of n, which is that one that will take n time, plus O of 1 again, which is for the return sum code block. At the end of everything, O of 1 plus O of 1, we're still going to talk about it. It's the same thing as O of 1. We can say 2 O of 1, but it's still O of 1. Because 2 O of 1 is still constant. It's like saying it takes 1 second to initialize an array, to initialize a variable. But it takes 5 seconds to test if the variable is equal to 0. Those two operations are constant time operations. Because it doesn't depend on any other thing. Like, no matter the size of my variable, to test it is 5 seconds. No matter the size of my variable, to initialize it is 1 second. So even though I add those two operations together and say they will take 6 seconds, both of them are still constant time operations because they don't depend on any other thing. Like, no matter the size of any other thing, no matter what any other thing we have, it's still going to take 6 seconds. So that's why when I say O of 1 plus O of 1, it's still basically O of 1 is just representing, don't see it as math numbers or math anything. It's just representing something which is constant time. So O of 1 plus O of 1 is still a constant time operation. Now O of 1 plus O of n is O of n. And the reason is, remember we said big O represents like the worst case. And now since O of n is bigger than O of 1, then the total runtime is O of n. So it means that in the worst case, so it will be O of n. So we just choose O of n. Right? So I said O of n because we assume the length of the array is n. So how about quadratic time? Quadratic time is written as big O of n squared. So let's say we have this function, and this function adds two numbers. But this function actually checks if two numbers in my array, the function takes in an array and the sum. So it checks if two numbers in that array is equal to sum. That's all. It just checks if two numbers in my array is equal to sum. And now, what this function does is, it starts from index 1, which is the second element in the array, goes to the end. For each index, it goes through the array again, basically goes through from 0 to 1, goes through the array again, and then checks if the number, which is first num is the current number, is equal to any of all those numbers, if first num, plus any of all those numbers is equal to sum. So we have first num equals array I, and then we are going through the array again from 0 to I. So we're checking if first num plus array j is equal to sum. So we're picking a number and then checking all the numbers before that number to check if the sum of any of them, my current number, which is first num, is equal to sum. So if it's equal to sum, I return true. But if I don't find that pair, I just return false. That's what we say at the end of the function. So I don't find a pair, I return false. Now let us analyze this line of code, this block of code again. So the first line, this time around, is going to run n-1 times. And the reason is, the first line I mean after the for loop. And the reason is, remember, the for loop is running from 1 to array.length, right? So it's not starting from 0. If you're starting from 0, then it's having n. It's not starting from 0. So it's starting from 1 to array.length. So that's like, it means that that first line in Snom is going to run n-1 times, where n is the length of our array, right? And n-1 time basically is an O(n) operation, right? It's an O(n) operation. I'll still talk about like the constants. It's not like O of n-1. It's just an O(n) operation. Then the if statement inside. I'm sorry for the way, I don't know why the formatting just destroyed, and then we now have things on each other. I should have tested this beforehand. So the if statement, if you can just look through that if statement, you check how many times that if statement run. That statement is basically going to run, say, for each time the inner for loop, that inner for loop is running I times, right? But I now is dependent on the outer for loop. So the first time I will be 1, that for loop, the inner for loop will run once. The next time I will be 2. Sorry, yes, the next time I will be 2, the inner for loop will run twice. The next time I will be 3, the inner for loop will run 3 times. Next time I will be 4, the inner for loop will run 4 times, till I is n-1. And then the inner for loop will run n-1 times. So it means the inner for loop is going to run 1 plus 2 plus 3 plus 4 plus 5 till n-1. And if we've done like summation of natural numbers in mathematics, it's just basically summation of natural numbers. So summation of 1 to n, but now we can now use summation of like 1 to n-1, which is equal to n times n-1 divided by 2. And n times n-1 divided by 2 is n squared minus n over 2. That's just n squared, big O of n squared. We'll still talk about that later, big O of n squared. So now return false. Return false also is a constant time operation, and that takes constant time, really, not depending on anything. So at the end of the day, by the time you add everything together, so runtime is going to be big O of n plus big O of n squared for the if statement plus big O of 1, which at the end of the day is big O of n squared. Remember, I said we are looking at the worst case. So big O of n squared is bigger than big O of n. That's why I'm picking big O of n squared now as an answer. Okay, so here we have logarithmic time. So this function takes an array. It takes an array, and all it does is it basically iterates through the array, but it does something different. It doesn't iterate through all the elements. It iterates through the array in a funny way, such that it's the index, the variable that represents the index is multiplied by 2 at each point. So at every time the array runs, that variable multiplied by 2. So let's assume, let's just take an example. Say the array's length is 8, for instance. At the first iteration, sorry, we need to make a change also to that code. Please, I'm sorry, I'm just saying it. Let's assume int I equals 1, not I equals 2, not I equals 0. Because if I equals 0, then the for loop will just run forever. Because it's going to multiply 2 by 0, and then it's still going to be 0, and it's never going to get to array.length. So I'm sorry for that. So int I should be equal to 1. So if I equals 1, then at first iteration, I is 1. Print Python suite. Second iteration, I is 2. Third iteration, I is now 4. Fifth iteration, I is 8. Now, 8 is not less than 8. So it means it's not going to print for the fifth iteration. So it means if my array size is 8, I'm just going to print 3 times. Right? I'm going to print when I is 1, I'm going to print when I is 2, and I'm going to print when I is 4. Even if my array size is 8. Now let's take it again. Let's assume my array size is 32. If my array size is 32, it means I'm going to print when I is 1, I'm going to print when I is 2, I'm going to print when I is 4, printing will be done when I is 8, when I is 16, and that's all. It means I'm going to print 5 times. Even if my array size is 32, I'm just printing just 5 times. Nice. Right? Now, if you check the rate at which the amount of times I'm printing is increasing, it's different from a linear time operation, like different from that linear search. For linear search, as I'm increasing the size of my array, the amount of times I'm printing is also increasing. Like if my array is of size 4, then I'm going to print 4 times. If my array is of size 5, I'm going to print 5 times. But if my array is of size 4, I'm printing twice. If my array is of size 5, I'm printing 3 times. If my array is of size 6, I'm still printing 3 times. 7, I'm still printing 3 times. 8, I'm still printing 3 times. So even if we go on to when my array is of size 1024, we'll notice that I'm just going to print 10 times when my array is of size 1024. And then, if we try to use like a mathematical expression to represent this, it's just log of n to base 2. Now let's look at it. If my array was size 4, I said I was printing twice, right? Now, log 4 base 2 is 2. So it basically represents that, okay, that my function just run twice, right? If my array is of size 32, log 32 base 2 is 5. So it still means that my function will print just 5 times. If my array is of size 1024, it means my function will also still print 10 times. That's log 1024 base 2. So that is why it is logarithmic time and log of n. So let's take, I think we have one more, which is exponential time. So we also have something called exponential time. Now we've talked about linear time, which is big O of n. We talked about constant time, big O of 1. We talked about quadratic time, big O of n squared. We talked about logarithmic time, big O of log n base 2. So now let's talk about exponential time. Now, exponential time is represented as any constant raised to the power of n. Any constants that we have raised to the power of n is exponential time. That's it. Any constant. So that I just wrote a raised to the power of n. I should have written where a is a constant. So it could be 2 raised to the power of n, it could be 3 raised to the power of n, it could be 4 raised to the power of n, but any constant, except of course 1 raised to the power of n, because 1 raised to the power of n is just 1. So any constant greater than 1. So it could be 1.5 raised to the power of n, it could be anything greater than 1 raised to the power of n. So looking at this line of code now, this basically is a recursive function. So we have a function f basically that takes in n, and then if n is less than or equal to 1, it returns 1. But if n is not less than or equal to 1, say if n is 2, it returns the function again for when n minus 1. It basically returns 2 times the function n minus 1, which is f n minus 1 plus fn minus 1. So if n is 2, it will enter the code and then check, okay, n is not less than 1. So it's going to go to the return statement, then it's going to return f of 1, calling the function again on 1, plus calling the function again on 1. So when we call the function again on 1, it's going to enter the code and check, is n less than or equal to 1? Yes, s is less than or equal to 1. It's going to return 1. So f of n minus 1, which is f of 1, will return 1. And then it returns 1, the second f of 1 will also return 1. So f of 2 basically returns 2. So we can go that way for f of 5 or anything. So if first to analyze this algorithm, because now checking it, we say, okay, if n, that if statement is a constant time operation, right? But then return f of n minus 1 is calling itself. Like we cannot just say that is a constant time operation because it is calling itself again. And then the amount of time it's going to use to call itself is based on n. Like we're not sure. So to analyze this, we need something different from what we've been using. So we're going to use something like a recursive tree, right? So now if n is 4 at the beginning, so that's what this recursive tree uses. N equals 4 for start. So if n is equal to 4, it's going to call itself for n equals 3 2 times. And now you can see 2 branches, left and right. For each of the n equals 3, it's going to call itself again twice. That's f of 2. For each of them, it's going to call itself again twice. That's f of 1. Then when it gets to f of 1, we can now finally get to the base case, which, remember the function, like if I go back, the function says if n is less than or equal to 1, return 1. So by the time f is equal to 1, then it's just going to return 1. So it means for this function to run, for just when n equals 4, the function is called 15 times. Now when n equals 3, so if you just look at that f of 3, n equals 3, the function is called 7 times. So from this we can infer that for any n, because 15 times equals 2 raised to the power of 4 minus 1. 2 raised to the power of 4 is 16. 16 minus 1 is 15. For n equals 3 also, 2 raised to the power of 3 is 8. 8 minus 1 is 7. Right? So we can infer that for any input size n, the function will be called 2 raised to the power of n minus 1 times. Right? Mind you, n has to be greater than, of course, n has to be greater than 0 or 1. N has to just be a positive integer. So for any number, so if we say, if n was, say 5, for instance, this function will be called 31 times. If n was 10, the function will be called 1023 times. And so on. That's how it's going to go. So the function will be called 2 raised to the power of n minus 1 times. So we can infer that the time complexity is not 2 raised to the power of n. Remember, we're trying the minus 1 again. Because we really don't care about minus 1. It's just a constant that doesn't even show us, it doesn't show us how the function goes. So we don't really care about it. 2 raised to the power of n, we'll still talk about it anyway. We'll still talk about it down the line. 2 raised to the power of n minus 1 is asymptotically equal to big O of 2 raised to the power of n. Right? So if you look at all what we just mentioned, you can even infer that some algorithms are like really terrible. So from linear time went to quadratic time. You can see quadratic time is like worse than linear time. Because linear time, if I didn't just draw a graph for that, say a for loop takes, I don't know, 10 seconds, if for loop takes 1 second and n equals 10. So it means the for loop would run 10 times, right? So it's going to use 10 seconds. For quadratic time, it's going to basically use, say, 10 raised to the power of 2. In the worst case, 10 raised to the power of 2, which is 100. So it's going to use 100 seconds. So same thing, the linear time algorithm that uses 10 seconds would use 100 seconds, sorry, if it were a quadratic time algorithm. And for logarithmic time, it's just going to be log of 10 base 2. Log of 10 base 2, I think, is going to be 3 point something. And then for exponential time, it's going to be 2 raised to the power of n, which is like 1000 or something. So you can see the sparsity, like how you can see the good ones and you can see the bad ones. Whereas a constant time operation, even if n is equal to 1 million, it doesn't care. If it was going to use 50 seconds before, it will see 50 seconds is going to use. So as n is increasing, exponential time is like increasing drastically. It's just straight, it's just, as one of my friends says, just blow up. So if n, imagine if n was 100,000, for instance, and then we're running, imagine it was 100, not 100,000, and they want to run this function. So this is 3 raised to the power of 100 minus 1. And that would be something like, I don't even know the answer, but it's a very, very large value. Why quadratic time be 100 square, which would be, I think, 10,000? Linear time would be like 100 seconds. Why binary search should just be probably around 8 point something second. So let's talk about some important points when dealing with big O. So you must have noticed that I've been dropping the constant. Like when I had like something running for n minus 1, I said it was just big O of n. So in big O notations, we don't care about constants. There's nothing like, say, big O of n minus 1. Big O of n minus 1 is just the same as big O of n. So even though it's big O of a times n, big O of n plus equal n plus or minus a, it's still equal to big O of n if a is a constant. Mind you, if a is a constant, why am I a constant? If a is like a number, say 200, 1 million, it doesn't matter. Big O of n plus 1 million is still the same thing as big O of n minus 1 million, which is still going to be big O of n. Do you get? So just write it as big O of n. We don't care about it. So I give the example that big O of n minus 6 is asymptotically equal to big O of n divided by 2, which is asymptotically equal to big O of 100n, which is also the same as big O of 1 plus 4, 3, 4, 5n. So no matter what happens, when you want to have a constant, plus or minus anything, it's still big O of n. Only if a wasn't a constant. Imagine I pass 2 arrays to my function. And then one was size m, one was on size n. And then after the analysis, I had like big O of n plus big O of n. I cannot just say the answer is big O of n. Because of m and n are not constants. So my answer will just be big O of m plus n. I'll try it like that. But I cannot have big O of m plus 1. Just big O of m. So also drop the less significant terms. Remember, I said we were working with worst case. So if I have something like, after the analysis, I have big O of n plus big O of n squared plus big O of n plus big O of 5, anything. Looking at this example that is here, the first one is big O of n plus big O of log n plus big O of 1. Now, big O of n is bigger than the rest of them, right? And remember, big O deals with worst case. So I'm just going to choose the biggest of them all, meaning big O of n. So we're not going to write big O of n plus log n or big O of n plus 1 or anything. No. Just choose the worst big O of n. Imagine we have something like big O of 2n squared plus big O of n times log n plus big O of n plus 5. Now, the most significant term there is 2n squared. So we just have big O of 2n squared. But remember from the former slide, we said we drop the constant. So it's just big O of n squared. That's it. So we drop the less significant terms. We don't care about the less significant term, just the most significant term. So if I had something like big O of 2 raised to the power of n in this second example, if I had it here, if I had like plus big O of 2 raised to the power of n, then that would have been the answer. Because 2 raised to the power of n is bigger than the rest of them. Remember, exponential time. By the time you do your 2 raised to the power of 100, it's bigger than n, it's bigger than 100 squared, it's bigger than 100, it's bigger than log 100 raised to 2. So the answer would have been 2 raised to big O of 2 raised to the power of n. That would have been the answer. So let's just take some exercises. So I'll just run through some examples, some exercises basically, but we'll do it together and then try to see what happens. So now, imagine we have an algorithm like this, or we have like a code, because this is in Java. So we have something like this, and then this function tries to get the minimum value in the array. It returns the minimum value in the array and the maximum value in the array. I don't know, my return statement is not sure, but basically, let's just say it calculates the minimum value in the array and the maximum value in the array. So the first line in the function is just initializing the variable. That looks like a constant time operation. The second line also is just initializing the variable. So that's also a constant time operation. Now the next line is the for loop. So it means that when we have in that for loop, and the for loop is going from 0 to array.length. So let's assume that array is of size n. So it means that for loop will run n times, right? So it means min equals min less than. That line of code that we have there is going to run n times. Then the second for loop also is starting from 0 and going to the end of the array, trying to get the maximum value. So since starting from 0 and going to the end of the array, and we assume that the length of the array is of size n. So it means that what we have inside that array, inside that for loop, sorry, is going to run n times also. I'm sorry, my formatting again. It's just terrible. And then there's supposed to be one, the return statement is supposed to be on that will just be a constant time operation. So at the end of everything, when you add all these things together, the C's there are just constant time operations. Big O of 1 plus big O of 1, n then will be big O of n plus big O of n plus big O of 1. So remember I said big O of 1 plus big O of 1 is basically still big O of 1. You cannot say maybe big O of 2 or anything, it's just big O of 1. And then big O of n plus big O of n, which is like big O of 2n. Right, so I have big O of 1 plus big O of 2n. So big O of 2n, remember we drop the constant. So it's basically big O of 1 plus big O of n. Now big O of n is bigger than big O of 1. So choose the most significant term, which is big O of n. And the answer to this will just be big O of n. Right? Even if we are iterating through the array twice, and then some people might tell you to say, okay, it's actually big O of 2n. But really, we just drop the constants. We don't care about the constant there. We don't care about 2 or anything, just because of that. So another one, which basically just prints numbers in an array. So we have like in 2 arrays, so we have 2 arrays, and then we are iterating through the array, right? So let's say array 1 is of size, let's say array 1 is of size m, and array 2 is of size n. Because now there are 2 different arrays, right? So let's say array 1 is of size m and array 2 is of size n. So the first system.out point line under the first for loop basically should run n times if array 1 is of size n, right? So it's going to run n times. And the second one, which is of size m, should run m times. Array 2 dot length is of size m. Now at the end of the day, so it means the first line is going to be like big O of n. The second one is going to be big O of n. Now, big O of n plus big O of n, you can see big O of n plus n. But now we cannot drop anything because m, neither m nor n is a constant. Right? If it's a big O of n plus 2, and I'll say the answer was big O of n. But now, n is not a constant, m is not a constant. So I can't drop anything basically. Because m and n are dependent on the input. So I'm just going to, so my final answer should just be big O of m plus n. One time, big O of n plus n. So the third one, I didn't already give the answer already. And doing it indented is just terrible. Okay. So third one is basically like a sorting algorithm. So it's selection sort. So basically just wants to sort your array. But we don't even need to understand the code. We can just follow, let's just analyze it line by line. Okay. So we have a for loop. And then the for loop is going from 0 to array.length minus 1. So it's going from say 0 to n minus 1. So it means that for loop, the first for loop will run n minus 1 times. So that line of code that is under, which is int main post equals 1. Int main post equals 1 normally is a constant time operation. But because it's under a for loop that is running n minus 1 times, so it means int main post would run n minus 1 times. So it means this is just n minus 1. But then I can still write it as big O of n. Right? Because remember, we jump the constants. The second for loop is now going from I plus 1 to the end of the array. Second for loop is going from I plus 1 to the end of the array. Now, let's start. If I, at the beginning, I is equal to 0, right? So it means the second for loop will go from 1 to the end of the array. So it means second for loop will run n minus 1 times because the array is of size n. And if you are going from 1 to the end of the array, so it means you run n minus 1 times, right? Because it's 0 index, you're supposed to be like starting from 0. So for the second time the for loop itself will run, that's the first, by the time the first for loop runs the second time, I becomes 1. And then j would go from 2 to n. So j would go n minus 2. And so on. So it means the second for loop will run, the first time is going to run n minus 1 times, then n minus 2 times, then n minus 3 times, then n minus 4 times, till I equals n minus 1. And then when I equals n minus 1, then j, then when I equals n minus 2, because remember, I is going to I less than n minus 1. So when I equals n minus 2, then j would run just once. So it means it's just going to go from n minus 1 to n minus 2 to n minus 3 to n minus 4 to 1. Which is basically still the same thing as 1 plus 2 plus 3 plus 4 plus 5 till n minus 1. Right? And remember, I talked about sum of natural numbers the other time. So that should just be, so basically this is it. So that line is just the summation from I equals 1 to n minus 1. And we are summing n minus I. Because the first time when I equals 0, we are going to run the for loop n minus 1 times. So it means this summation sign would go n minus 1 first. It's going to go n minus 2 when I equals 2 in this summation sign, and n minus 3 to when I equals n minus 1. Then just going to be 1. Right? That's n minus 1, and that just be 1. So that's the amount of times I will run. Also, the mean post equals j. I'm sorry for the indentation again. It's just, I don't know. I did it well, but I don't know. Presentation would just show everything. And then for this one that's saying n, that's for instemp equals array I. Now if we look closely, we'd see instemp equals array I is not under the second for loop. It's just under the first for loop. So this is under the first for loop, and then we are sure the first for loop is running n minus 1 times. Then it means that instemp equals array I will just run n minus 1 times, which is basically O of n, right? The second one also, array I equals array main post is also going to run n times, n minus 1 times, which is still big of n. And the third one also is still going to be the same thing. And then the way you add everything together, look at it. We have n, which is big of n. We have summation of basically that is a summation sign, which is that summation sign is just n open bracket n minus 1 over 2. we talked about in the previous slide, and that's basically n squared minus n over 2. Remember, we take the significant terms, so big of n squared minus n over 2. We don't care about that n because my n squared is bigger than n. So it's the same thing as big of n squared over 2. And then 2 is a constant, so I don't care about 2 also. So basically the same thing as big of n squared. So it means that that second arrow we can see, the time complexity for that line of code is just going to be big O of n squared. Also, the third arrow, big of n squared, and the fourth one is big of n, fifth big of n, sixth big of n. By the time we add everything together, we have big of n plus big O. We have big of n, I think, 4 times, which is big of 4n plus big O of 2n squared. Now we'll drop constants, so we have big of n squared plus big of n, and then take the most significant term, which is big O of n squared. So that's why this is big of n squared. So this is the idea of this is just basically just show us how we can analyze our algorithms, and then we can represent them in big O format. And as we've explained that big of n, we can see now that big of n is worse than big of log n, because as if n equals, I don't know, 1024, then our code will run for 1024 seconds. You can see it as our code run for 1024 seconds. It doesn't necessarily mean that. Why log n, we run for just 10 seconds. I really want to do it faster. So that means big O of log n is better than big O of n. Big O of n in turn is better than big O of n squared. Big O of n squared in turn is better than big O of 2, which is 2 raised to the power of n. So this is just the whole concept of understanding how the big O notation works, how we can use to analyze our algorithms, and basically in the next lectures or in the next series of, I don't know, next series basically, we're going to talk about how we can optimize all these particular algorithms so that we can do better. So our algorithms are like that other one that is like exponential time, big of 2 is power of n. We don't wait forever to do a particular thing. We don't want to write functions or write code such that our users will have to wait for 100 years if the input is so large. We don't do that because then we frustrate our users and they'll never ever use the platform again. So these are the things that they would ask us in interviews. These are the things that they'll look at in interviews when they ask us to like do a particular thing. They expect us to analyze the time complexity of that thing, to understand how fast this would run. So that's just the idea of understanding the big O notation. You can understand how fast this runs in the worst case, and then we can basically optimize it to better. So the resources that I'm going to advise us to use, because the idea of this is basically just for me to just do the introduction, and then hopefully we still go on to go and read to understand better. So the resources I'm going to advise us to use is Cracking the Coding Interview. So Cracking the Coding Interview is a very, very good book. Very, very good one. I advise that. For us that probably wants to dig little into the math, want to understand some math behind the big O, I'm saying just throw this on away over 2, and it's not agreeing with your soul, then you can just check the math in Introduction to Algorithms by Comment. That's a very, very good book. You can download it and then you can check it. And then if, I don't know, you still don't like reading, you don't like reading, and then reading is still not your thing, and you tried reading, you still didn't understand, you can check out this lecture series, Introduction to Algorithms, MIT OCW. So just check Introduction to Algorithms and then check for time complexities or something. So it's well explained there. So you can check this before probably the next series. So you need to understand the big notation so well, and then by the time an algorithm is given to you, you can analyze and say, okay, it's big O of n. Okay, it's big O of n plus n. Okay, it's big O of n squared. And then once you understand this, then you can understand the difference between a good algorithm and a bad algorithm, and then you can basically know when to optimize and write better code. So thank you so much. If you have any questions, I can take questions now, and probably if during the week or when you're reading any of those resources, you still have some questions, you can just use the Slack channel, and then just, I think Hope mentioned it, and then just ask to me, or just send me a DM on Slack chat. I would try my best to respond in time. Thank you very much.
Thanks, Timilein, so much. Thank you very, very much. Like, this was an insightful session. I mean, yeah, I don't know about what that was for you. So, we don't have much time left. So, if you have, we can take one or two questions. If you have any question right now, feel free to unmute and drop your questions. Yeah. So. And please, just like I said earlier, while you're thinking of your questions, the slide will be shared via the Slack channel. So we'll be dropping the slide on the Slack channel. We'll be dropping links to resources on the Slack channel. And you can also reach out to him on Slack channel in case you have any question or anything. So please feel free to ask your questions now. You can unmute and ask your questions. Okay, nobody's talking. Is it that we don't have questions or what?
No questions.
Okay. Okay. Okay, even if you don't have question, I want one or two people to at least acknowledge they learned something, or just to be at least, because we need to know that you got something from this session and at least you have something to go back home with.
I think some people are putting stuff on the chat.
Oh, okay. Oh, okay. 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 Thank you so much. Okay. Okay. So I want to believe we learned from this. I mean, I learned a lot. And please, 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 I know we are all quite busy, and I know we can always get busy, or we can always try to always sideline things, but try as much as possible to read more on this concept. I mean, you may not have gone in depth, or you might have gotten to a point and you felt swayed away by what he was explaining. Like, oh my god, what is all this one? Please try as much as possible to go back online with the resources that will be shared. We're sharing the slide this night, so you'll get it. Go back online and read more about it. Try and understand, at least have a basic knowledge about it. Because I mean, it will help you in upcoming series, so that when we start speaking in terms of, okay, no, this algorithm what's the time complexity? It is order of n square. It is O of n square. And somebody, you're like, so that you will not be looking at me like, okay, what is this one again? So please try as much as possible to go back and read more on it. And just like you said, you can always reach out to him on Slack. He would always answer your questions. So I want to believe nobody has any other question or any other thing. So Dami, over to you. I think you can close the.
I think someone has a question. Chichuku.
Oh, okay. Similarly, somebody has a question for you.
Okay, that's fine. You can go ahead to ask a question.
No, the person already said it on the group chat.
On the chat
section.
Okay, serious. Okay, let me open that.
He said, okay, can you listen to me? He said, is it necessary for a complete newbie to understand algorithms and data structure at an early stage?
Okay, so the way I say it is, if you're a complete newbie, then probably the first thing for you to do would be to basically first understand the concept of programming in the first place. Just understand programming itself, and then choose a particular language. Then probably just learn some syntax in that language. Now, once you understand the syntax in the language, then yes, you should start learning algos and data structures, because that's the way for you to solve problems optimally. Because then I just see a lot of people basically learn programming, and then they've learned this framework, and then they can just write code in this framework, and they can do this and that. But they don't even understand. They don't even know how long it takes for their code to run. They don't understand all these things, and these things are really, really important. Because you don't want to, as I said, you don't want to write codes that will get users frustrated. You don't want users to spend 10 hours or, I don't know, 5 minutes staring at loading screen when it would have been done in a very, very short time. Or you don't even want your company to spend lots of money buying so much resources, where you could have still used very, very little resource for that same software. So that's why it's key and it's very important that you learn algos and data structures, because algos basically will teach you how to solve your problems optimally, and for you to know even an optimal solution, then you need to know G-code notations. You get, and data structures will also do the same thing. I hope I answered your question.
Okay, Stacy, you say you have a question. You can feel free to unmute and still ask your question.
Okay, good evening, everyone.
Yeah, we can hear you.
Is there a way to identify the least worst time for a particular problem? Like say searching, like is there a way to know that, okay, something better than linear search would be binary search, which runs in logarithmic time, I guess, log n? Like, is that a way just by looking at the question, you should know that, okay, this thing shouldn't, like the best worst case you can do, if that's even right, is not linear time. You can do something better than linear time.
Okay, hello, Stacey. Very good question. Now, for you to know this, for you to just see a question and just know that, okay, I have an algorithm in my head, and that algorithm is, say, linear time, and then I think I can do better. I think this question should be solved in, I don't know, logarithmic time or something. It basically takes practice. You can't do that like just learning. It's not just magic. I can't just wake up one day and be like, oh, searching can be done in log n. Like, it just takes practice. Now, the more questions you practice, the more algorithms you know, the more. Now, when you learn algorithms and data structures, you're not just learning to cram, you're learning to understand how to solve problems. So once I learn these things, and once I've solved lots of questions, then when I just see this problem, I'll be like, I think I've seen a problem that is similar to this. Or this problem just shows some properties. This problem just has some things. Like, I'll just see searching, and then I can see that probably the array is sorted in this way. And then, because I've solved lots of questions, I know that anytime it involves sorting, like really, I can do better than just searching. Because really, then what's the difference if it is sorted and it is not sorted? So this question, for you to know, it has to do with experience. You have to have solved lots of questions. You get, because I'm sure first time I was supposed to like maybe search in a sorted array, and I'm sure it was linear search I used. I did not think of binary search. I'm sure it was linear search. But as I continued and then I was able to learn binary search, I'm like, oh, this makes sense. And when I want to sort now in an array that is not probably even sorted, like, or it is sorted, but it's not sorted perfectly, let me know that, okay, I can do better than linear search. And then try to think of a better way to perform the operation. So, in answering your question, basically, it lies on experience. When you solve plenty questions, and then you understand algorithms and many data structures, then you would be able to know. I've answered the question.
Yeah,
okay,
then,
sorry,
follow-up question.
I want to contribute to Timmy's answer. Okay. Sorry, can I speak?
Yeah.
Stacy, also, with what Timmy said, Timmy is right, but also there are some questions that like give off their answers directly just from reading the questions. Like some questions come with hints. For instance, you're given a question and it says, giving a list of sorted blah blah blah. For you to know that the list is sorted, then there is an incentive to use a binary search, because binary search deals with sorted items, you get. So some questions give off answers just by reading the questions. So it takes practice, like Timmy says, but it also takes incentive to it. Like you have to really understand the question before you start solving. That's another way of like getting around time.
Thank you. But I have a follow-up question, which is like in calculating the running time for a code, like if you're using inbuilt functions, but you don't exactly know the running time for the function you're using, how would you calculate that?
Okay, so if you're using an inbuilt function, so that's actually one of the reasons that probably if I go for technical interviews, I really don't just use inbuilt functions without knowing the time complexity of the input function. First and foremost, there's this concept called BCR, which is best conceivable runtime. So best conceivable runtime just means that this is probably like the best time that this thing can happen. Like, I cannot do it better than this. For instance, say you want to sum all the elements in an array. You cannot do it better than O of n, because you have to go through all the elements in the array. So if I see a function, an inbuilt function called sum, for instance, without even knowing the function implementation, I would infer that this function should be O of n, because that just makes sense. Like, that's like the BCR. I cannot do better than O of n, because I have to go through all the elements in the array. Do you get? And as I said, that's also one of the reasons that if I see like something, probably if I'm an interview, I see something that, okay, I can write, and then I'm really not sure of the implementation, I can use the input function and tell the interviewer that I'm not really sure of the implementation of this, but I probably can do it in O of log n. And if it's not bothered about that, if that's not like really part of the question, you tell me to proceed. But if that's like the cocoa of the question, like say it told you that you should search in an array, search for elements in an array, I wouldn't advise you use an inbuilt function, because it probably wants to see the implementation itself. And I'll probably just want to write my binary search by myself, not to just use inbuilt functions. So I try to shy away from inbuilt functions if I'm not really sure of the time complexity. If I cannot infer like in the BCR, I'll say I'm not really sure, I'll probably just shy away from it. But if I know like the BCR, like say sum now, I'm sure that that's be O of n, something like that. Maybe searching an array and the array is not sorted, I'm sure that it's still O of n, things like that. And I'll probably just want to write my own if I'm not sure of it. Do you get? But if it's like a sorted array now, I probably not want to use Python search, but I don't know if I'm going to use binary search in it. I'll probably just write my own binary search and then do it. So you cannot, or if you want to read the documentations, because I'm sure there are documentations, the language they're using, and they can just read documentations where it's been shown the time complexity. Like, I think there are some options Python will actually tell you the time complexity in the documentation, but then you have to implement it. And then you can now know the time complexity of these things. But as I said, if I'm not sure of the BCR, I'll mostly just shy away from it and then write myself.
Okay. Thank you, Timile. Yeah, thank you, Stacey. We've run out of time. Yeah, we promised to end this by 8. We've run so much out of time. So please, if you have questions, always feel free to reach out to Timile or any of the facilitators on the Slack workspace. And thanks so much for joining this call. And please, just like they said, I know some of you may have been blown away today by, to some people, this may have been jargons like, what is all this one? Really? Please, and please don't run away. Don't be like, hey, I've never said anything. See what they are saying. See all this code. See all this language. I mean, don't get blown away. Just like he said, practice makes perfect. I mean, you need to practice a lot of things. You need to nobody just woke up one day and became perfect in telling time complexities of algorithms. No, it's as a result of practice. So please, and please don't run away. Still stay with us for this series, and I'm hopeful and I pray that you would, as time goes on, you would get better in all this. So thanks so much once again for joining the call. We hope to see more of you on Slack, and we hope to see you again.
I'm sorry, I'm saying one more thing before we leave, which is as Hope said, you shouldn't run away because of probably the old time complexity because something was basically nonsense to you. The thing is, we'd continue to use it in this series. Like next week, the person that would probably anchor the next session teaching on arrays and strings would teach these things and then also tell you the time complexity for different operations. So continue to stay hammer on this same topic. So it's not something that you probably understand right away. Do you get? Just something that we just have to do the introduction. So by the time I was saying it in the next session, it's not going to look like too much nonsense. So next session, we'll still continue to hammer on the same point. We'll still continue to hammer, we'll still continue to do the same thing. And hopefully by the time we're done with the series, you have understood perfectly the time complexity of a particular algorithm. You to calculate that yourself. Hopefully also you have understood some other things too. So as Hope said, please don't run away. Next week also, we'll still go on and I think arrays for strings.
Let's see you next week. And next week is going to be interesting. It's going to be fun, and it's going to be easier than this. I hope it's going to be easier than this. Yeah, please, the Slack workspace is The link to the Slack workspace is somewhere on the chat. Please join if you have not joined before. Please join now before you leave this call, or copy the link somewhere and join later. But please try as much as possible to join the Slack workspace. It is very, very important. Yeah, I think I'm trying to post it again. And with that, we have come to the end of today's session. Thank you for joining, and we hope to see more of you next week.
All right, bye. Thanks so much, guys. Have a lovely night.
Yeah, screen grab. Screen grab this.